Now let us take another problem which can be solved applying Kirchhoff's law. Now look at the circuit shown here, and we have to find the current in each of the branch. Now you can see the resistance of each branch is given. Here resistance is 0.02 ohm. Here resistance is also 0.02 ohm. Here 0.03 ohm, and here the other resistances are also given. And incoming current to a junctions and is also given for each junctions. Now I have redrawn the circuit here. I have named each of the junctions and I have given the direction of current in each branch randomly, and I have named it also, the current I have named it. And now if you apply the Kirchhoff's current law at the junction B, then you can see I is incoming and 80 and I1 is outgoing. Therefore, you applying the Kirchhoff's current law, you will get I minus I1 minus 80. Therefore, you can say I equal to I1 plus 80. Therefore, here we are getting equation number, and here getting this applying at B. And from that, we getting I1 in terms of I. Therefore, our intention will be express each branch current in terms of I. Therefore, now we will applying the same thing we will apply at Kirchhoff's current law will apply at the junction C, and here you can see that I1 and 90 is incoming. Therefore, I1 and 90 is incoming and I2 is outgoing. Therefore, we will get this equation. In this case, we already know I1 in terms of I. Therefore, we replace that I1 and from the equation number 1. Therefore, we'll get the equation number 2. Therefore, you can see here I2 we have expressed in terms of I. Exactly in the similar way, we'll apply the Kirchhoff's current law at the D, and then we'll get this equation, and we'll see that I3 will express in terms of I. And you can see now we'll apply the Kirchhoff's current law at E, and we'll get I4. We'll get I4 in terms of I. And lastly, applying Kirchhoff's law at F, we'll get I5 in terms of I. Now you can see all the branch current is converted into in terms of I. Now we'll apply the Kirchhoff's voltage law. In the Kirchhoff's voltage law, in A, in the clockwise directions, we'll take in the clockwise directions. Therefore, A, B, C, D, E, F, and A. Therefore, here there is no batteries, no voltage source. Therefore, it will be, if along the direction of current, it will be a negative I into R. Therefore, R is already given. Already I showed I is, therefore you can see the minus, this is the resistance into I. Here also the second branch, this is the branch, you can see this is the branch AB, and resistance into current into resistance, and resistance into current, and in the BC, CD, then this is DE, then EF, and FA last. And therefore this is, according to the Kirchhoff's voltage law, algebraic summation of the product of current and resistance and the EMF is equal to 0, and there is no voltage source. Therefore, in this loop. This is the equation, total equation. And if we simplify that, we'll get the value of I. We'll get the value of I as this is 48.2 ampere. And then after getting I, we can find all these values I1, I2, I3, I4, and I5 from the equation number 2, equation number 1, 2, 3, 4, 5. All these values we can find it out. And one thing to be mentioned here, that I1, we are getting I1 as negative. It means that whatever the direction I have chosen, the actual current flowing in the opposite direction, but the magnitude remained the same. Here I2 is a positive, therefore whatever the direction has been chosen, the direction is the same direction actual current is flowing, and magnitude is the same. Here it is minus 91.8, therefore direction is opposite, but the magnitude is the same. Here exactly similar, I4 is this. Therefore we found out I4 is this, and therefore we found out all these branch current and with the actual directions. If it is negative, whatever that we have chosen, it is in the opposite direction, but the magnitude is the same. And that is all about this problem.